at creating a quadratic with radical roots. So we have our quadratic, and these are the two roots. And the roots of a quadratic are talking about x-intercepts. That's what they call roots of any quadratic. Okay, so let's say we're on our plane here. What it means is we have some root here, and it probably looks like this, or it could be facing the other way. We're just kind of unsure. But these are the roots, okay? And they've given us the values for the root. The first root here is at 3 plus positive 7, so it's somewhere on the positive side. We don't exactly know what it is. And 2 minus 11 is going to be somewhere on the negative side, minus 11. Okay, so we're not used to seeing numbers written this way. And you could, if you really wanted, if you find it easier, you could actually go ahead solving what these are. So you can do 2 subtract root 11, and it gives you a value. And it's a really long decimal value, and that's why we'll usually keep things in radical form, because this is a lot simpler to write. So you could do that for both of these and find out exactly what the roots are. So we have roots that are some decimal values, okay? And this will be our second root. They've told us that this quadratic also passes through some point, and this point is an x and a y value. So if we're going to create this quadratic, what they've given us are x-intercepts, okay? Like we said, we have 2 x-intercepts. And the easiest way to create a quadratic with x-intercepts is to use what's called factored form. Have you guys used function notation? Have you used f at x is equal to stuff?
Yeah.
Yeah? Okay, so we have f at x is equal to, and the factor form is usually written like this. F at x is equal to a bracket x minus r and s, they call these letters, okay? And the r and the s are the roots, right? And you can call this r and this s or vice versa. It doesn't actually make a difference, okay? So all we have to really do is plug those values in for the r and the s, okay? So this function is equal to the a value with x, subtract, and what I'm going to do is I'm just going to actually input these almost in brackets of themselves, because it's actually kind of important when we do this. So 3 plus negative 7, so when you think of it, I'll write in blue so it looks a little different. 3 plus root 7, okay? And again, that's just some value, right? It could be like 2 point something, something, something. We've just written it that way. And x subtract 2 minus root 11. So these are the roots, okay? And if you had integers like 2 and 1, you would just replace this with the number 2 and the number 1, okay? Now, in order to solve for a, this is where it gets a little more complex. We need to solve for a, so we need a little bit more information. There's technically 3 unknowns right now. We don't know what an x value is. This is the equivalent of a y value of x, right? And we don't know the a. In order to write a quadratic, we need to find out our a value. It's fine if we have a y and an x in our equation, but we need to find the a value. Luckily, they've given us a point. This point here, these two numbers represent the x and the y. Okay, so we'll kind of highlight them. The first value, negative 8, is the x value. Okay, and the second value, 14, is the y or the f at x value. So we're going to replace them with those numbers. Okay, so we'll have 14 is equal to, a is still unknown, and this time x, we're going to substitute in for x. We'll do it in red here, so negative 8. Okay. Now I'm going to just distribute this negative. Technically, it's a negative on the outside of brackets. So if you remember distributive property, think of it like it's negative 1 times both of these. So this would become negative 3 minus root 7. Okay, because we're distributing that negative into those brackets. And it's the same idea if you had positive 5. Okay, when you plug it in, it usually looks like negative 5 in a quadratic. That's where that idea comes from. Okay, so we distribute it, and we would get negative 3 negative root 7. Okay, bracket. And then for the other x, again, we use negative 8. That's the x value we're replacing. And same idea, there's a negative in front of it. So think of it like we're distributing negative 1. So we're going to have negative 2 plus root 11. Okay, and negative times a negative gives us a positive. Okay, so we've got a whole bunch of numbers in here. We need to solve for a. We're going to do it using radicals, and in the very end we can calculate some decimal. If at this point you found it easier to use decimals, again you can just kind of convert your values. So we need to put these together. When we go to put these together, we're going to have 14 is equal to, I'll just write everything in black from here on. Because there's no more multiplication, I can just start putting things together. So negative 8 and negative 3 is going to give us negative 11 minus root 7, okay, times, and this will give us negative 10 plus root 11. Okay. Now these are values that can be multiplied by each other. So this is where the simplifying radicals kind of comes in. Okay. Technically, if you were to put this in a calculator, you get some number times some number, and then we would just divide. Okay. What I'm going to do is I'm going to simplify it and then divide after. So this is where you use your FOIL. Think of it like these two terms. Okay. So we got to take this one and multiply it by both, and we got to take this value and multiply it by both. So we get 14 is equal to A. Okay. So negative 11 times negative 10 is going to be 110 positive. Okay.
Yeah.
We have 110. Then negative 11 times positive root 11, we can't quite simplify, so we'll get negative 11 root 11. Okay. Here we get negative 7 root times negative 10, so that's going to be positive, and negative times a negative is a positive. And the 10 becomes like a coefficient with the radical of root 7. And then finally, it would have been nicer if I used actual radicals, so we could have simplified better. But a negative times a negative is a negative, and it's just going to be root 7 times root 11. Okay. So this is a little confusing. In this, I've chosen both prime numbers. So these are both prime numbers. There's nowhere we can break them up. So this is actually as simple as this is going to get. And the reason being is because you have a root 7 and a root 11, and you don't really have that occurrence happening anywhere else. So the next step to find A is you would technically bring this entire bracket to the other side. So you'd have A is equal to, and that's not going to be enough room. Move this over. A is equal to 14 divided by, I should have used much nicer numbers here, everything in that bracket, because it's technically multiplied. So when you bring it to the other side, you divide. So it's 14 divided 110 minus 11 root 11 plus 10 root 7 minus root 7 root 11. So a little confusing on the bottom here, but you can plug this all into a calculator and find an actual A value. Okay, and you could have done that off the start. I'll see if I can do it quickly here on one line. So we have the number 14 divided by, we need in some brackets, 110 minus 11 times root 11, okay, plus 10 times root 7 minus root 7 times root 11. I know the computing part is a little tedious. And we get some value, and the number is roughly 0.15. Okay, so your A value is 0.15. So minus all that radical stuff, where we had to multiply them all through, we would technically build our equation. And our equation would read f at x is equal to, this is our A value, so 0.15 approximately. And then we would just write the rest of our roots. X subtract, and I'll go back up to the top here, 3 plus root 7. So 3 plus root 7. And then x subtract the other radical, 2 minus root 11. So again, it would have been nice if we could have got some nicer values to work with. But this is what's considered the factor form of a quadratic. Okay.